Neutrinos are probably the most mysterious particles in the universe. The reason they're so mysterious is they pass through matter very easily. So there are trillions and trillions of them passing through every one of us all of the time, and they just go straight through. And that makes them very hard to study. But there are more neutrinos than any other kind of particle in the whole universe. So they're very special particles and they're absolutely everywhere. Over the last 20-25 years, we've started learning something about the properties of neutrinos. It's taken a long time just because of the fact that they're so difficult to detect. There isn't just one neutrino, there are 3 different types of neutrinos, and we call those flavors. That's a bit of a strange name. The way you can think of it, there's one type of neutrino, we call it an electron neutrino, but it's just one type, and there's another type, which is a muon neutrino. And what we found is if we take a particular type of neutrino and fire it over a very, very long distance, hundreds and hundreds of miles, it changes. So the way we've been doing our experiments recently is we make a very powerful beam of neutrinos, and then we fire that towards a very large detector, usually underground, and then detect the neutrinos and look for the way they change their flavour. And by doing that, we can measure their properties. Now, at this point in time, we know quite a lot about neutrinos, but we don't know everything. And we're starting to plan, we're starting to build the next big experiment in neutrino physics. And this is called the Deep Underground Neutrino Experiment. So this is like similar in style to our previous experiments, but much, much bigger and much more powerful. So what we're going to do is we're going to take a beam of neutrinos created at Fermilab, which is about 30 miles outside Chicago, and we're going to point our beam down into the ground, and we're going to point it towards South Dakota, which is 1,300 kilometers or 800 miles away. So it's a very, very long distance. So it's by far the longest baseline, the longest distance we've fired neutrinos over before. And in South Dakota, there's a very historical mine called the Homestake Mine, and there's a research facility already existing underground, 1 mile underground, called the Sanford Underground Research Facility. So what we're going to do is we're going to build 4 enormous detectors, really huge detectors underground, to detect the neutrinos we fire at the detector from the beam. So each one of these 4 detectors is about the size of an Olympic swimming pool, but 6 times deeper. So that gives you an idea of the scale. They're very, very big. And they're filled not with water, but they're filled with liquid argon. So it's very, very cold. And liquid argon enables us to see the neutrinos when they interact. So most of the neutrinos will just pass straight through these detectors and do nothing. But a few times a day, one will actually do something in our detector. And using liquid argon enables us to see all of the particles that come out of the interaction in beautiful precision. So we actually see in real time the neutrino interactions. And we effectively take a video of what's going on inside these huge detectors a mile underground. So that's the general idea of the experiment. And what we're trying to achieve, well, there are lots of things we're trying to achieve, but one particular thing we're trying to understand is why there is matter left over in the universe. So we kind of know now that if you look around this room or any other place in the world, we're made of matter, not antimatter. And that's a bit of a problem theoretically, because at the start of the universe, there was the Big Bang, and you create matter and antimatter in equal parts. It then goes and wanders around the universe, and as the universe cools down, the matter and the antimatter should come together, just disappear into light. So nothing should be left over except light. That's clearly not what we've got now. So something early on in the universe happened that made an imbalance, took away a little bit of the antimatter in favour of the matter, so something was left over. So that process we called CP violation, and it's the thing that leads us to a universe that has matter left over. Now we believe, or there's reason to believe, that neutrinos might be the explanation for this leaving over the bit of matter. So one of the things the Deep Underground Neutrino Experiment is going to look for is to try and detect this difference between matter neutrinos and antimatter neutrinos. So first we fire a beam of neutrinos at our big detector, and then fire a beam of antimatter neutrinos and look at the fundamental differences between those interactions. And by doing that, we hope, and we think we will, discover CP violation in neutrinos, and that will provide further evidence for this explanation for why there's matter left over in the universe.